Hello everybody, you are most welcome to this second video about dark matter and a yet undiscovered source of gravity. In general relativity, gravity is not a force. It is a geometry of spacetime itself. That geometry is sourced by the stress-energy tensor, which contains not only mass density but also momentum flows and stresses. Matter follows the geodesics in that curved spacetime. The key point of CRAG is as follows. Gravity can have multiple contributions depending on the geometric structure of stress-energy tensor. In other words, coherent rotation of mass and only this phenomenon in a specific regime gives rise to an extra curvature of spacetime. And this is what you can see on the pictures. On the left there is chaotic motion and on the right you see coherent rotation. Be aware of the fact that the spiral arms in non-Newtonian galaxies can go up to about 200 to 400 kilometers per second or about 1,000,000 kilometers per hour. Gravity appears primarily in thin, rotationally coherent disk galaxies and is weak or absent in dispersion-dominated systems such as ellipticals or irregular galaxies. Within the observed regions of these galaxies, no dark matter component is dynamically required to explain their motions. Any viable explanation must therefore account for both the effect and its selectivity. And now we come to the mathematics behind the augmented gravity. The CRAG framework introduces a minimal extension to the baryonic gravitational field. It does not add new particles nor modify Einstein's equations. On this slide, you see how we can derive the primary term for rotating galaxy disk from Einstein's field equations in 4 steps from energy stress tensor to mass, density and speed. This accounts for the contribution of coherent rotational motion through structure and the stress-energy tensor. The mathematical form in CRAG reflects how effective mass, coherent angular velocity and galactic scale combined shape spacetime geometry. The radial dependence summarizes how disk-like geometry alters curvature compared to spherical mass distribution. We have tested these mathematics with the SPARC database, and as you can see, the results seem to be quite consistent. The rotation curves show how CRAG compares directly with observations. The blue points represent measured velocities, and the baryonic contribution alone falls short. Mond and CRAG both enhance gravity, but CRAG does so through coherent motion of observed matter. These examples are illustrative rather than optimized fits and demonstrate that CRAG reproduces the main dynamical trends without invoking dark matter halos. The third part of our video. What does all of this mean for cosmology? Recent James Webb observations reveal massive rotationally supported disk galaxies already in place within the first billion years after the Big Bang. In standard models, such rapid assembly is difficult to achieve. With CRAG, enhanced gravity from coherent rotation naturally leads to shorter dynamical times and faster assembly. The curves shown here are schematic and illustrate a qualitative difference. CRAG allow galaxies to mature significantly earlier than expected in conventional models. This table is not a score chart. It shows that CRAG addresses the same observational phenomena as dark matter and modified gravity models, but from fundamentally different physical starting point. Again, it is a conceptual comparison, not a precision fit evaluation. On this slide, you can find our references with very interesting documents. Just keep in mind, imagine gravity is shaped not only by how much matter exists, but by how coherently it moves. Extra gravity emerging from coherent mass motion instead of unseen particles with adjustable halo profiles. We will now conclude this video about gravity emerging from coherent motion of mass. Perhaps this is a more obvious direction for further research. Thank you very much for your attention and your patience. We will look forward to your reactions.